Today we're going to take a look at the factor theorem. The factor theorem is a theorem that we will use extensively in this course. It is a theorem that allows us to take a polynomial equation, like we see here, which in this question represents the volume of a block of ice, and be able to determine or try to determine what the factors might be. These factors in this question are important because they help to determine the possible lengths of sides given a set volume. But we'll get to a question like this in a few minutes. Let's take a look at how we might use factor theorem. And one of the ways we will use factor theorem is actually spend a few minutes looking at the remainder theorem. The remainder theorem, as we saw in our previous lesson, allows us to very quickly determine the remainder. And that's really all it's good for. But this is a very important bit of information. I'm going to try and find the remainder when x is equal to positive 1. And the remainder theorem says that we replace each of the x's with the number in question and solve. And the end result in this particular case is 0. This is very important, as we'll see in a few minutes. The second part of the question is asking us to determine the quotient. And at this point, the way we determine it is by long division. So we would set up our long division question as we normally do, making sure that each of the degrees go down by 1, which they do in this particular question. And we would continue the long division process of, once again, asking ourselves, what do we need to multiply x by to get x cubed? And the answer to that is x squared. Because it's a binomial, we put it after the second term in the dividend. So that would become x cubed, x squared. And we would distribute the x squared through the binomial. First term should be x cubed minus x squared. The operation is subtraction. First terms disappear. 2x squared subtract a negative x squared, 3x squared. Bring down the following term and repeat. Once again, what is the number that we need to multiply, or the term that we need to multiply x by to rid ourselves of 3x squared, and this time it's 3x. And we distribute that through, and once again subtract. First term disappears, which is what we want. Negative x subtract a negative 3x is really plus 3x, so we have 2x. Subtract 2, the last term we brought down. Again, I can look at this now and say, well, I need to multiply the x by 2. And what I see is when I do my subtraction, the first terms disappear and also the second terms disappear, which we already knew because that's what remainder theorem forced us to do. And this is very important because what it means is x minus 1 is a factor of the dividend. The quotient is part of the answer as well. So the next question is going to ask us to write a statement which can be used to check the division. And what it means is that another way of writing x cubed plus 2x squared minus x minus 2 is x minus 1 multiplied by x squared plus 3x plus 2. So we have a factored form of our original polynomial. So we've taken a cubic and we found out that x minus 1 is in fact a factor, and this is what the factor theorem starts to tell us. The last part of this question is an important one because we always want to take a look at, in this case, the quadratic to see if it is also factorable. Because at this point right now, this means that x cubed plus 2x squared minus x minus 2 has an x-intercept at x equals 1. It crosses the graph at x equals 1. We want to see if there's any more. Remember that all odd degree polynomials must cross at least once. So I'm going to rewrite the first binomial, and then I'm going to look at x squared plus 3x plus 2. And I see through simple factoring of a trinomial that x plus 2 and x plus 1 are factors of the quadratic. This reveals for me that I have x-intercepts at x equals 1, negative 2, and negative 1 coming from each of the factors once we set them equal to 0. think of this. Now we are able to take a polynomial, and using remainder theorem and factoring techniques, we can actually figure out where the x-intercepts are. Let's take a look at a couple other examples. We have a little bit more complex polynomial, and the question is we want to determine whether x minus 2 or x plus 2 or x plus 1 or x minus 1 are factors. And to do that, recall that we need to use the remainder theorem, or really what we're going to start to call the factor theorem. Factor theorem is much like the remainder theorem. The only thing different is our objective is to find something with a remainder of 0. We can go ahead and plug in 2 wherever we see an x and solve the question. And once you do the calculation, this does work out to be not 0, which is really all we're concerned about. So when we multiply this through, I'll try and do it underneath here, 2 multiplied by 8 plus 3 multiplied by 4 minus 6 minus 2. And I can just do this in my head. I've got 16 plus 12 is 28. Well, 28 minus 8 doesn't give me 0. It actually, in fact, gives me 20. But I don't even need to finish this, because once I know it's not equal to 0, I know that x minus 2 is not a factor. And then I can continue with my next one. Let's try p at negative 2. And we will repeat once again. This time with negative 2. And once we do the quick math, this term does simplify to become 0. So this is a great time for us, because we can now say that therefore x plus 2 is a factor. And if we wanted to determine if there were more factors, we could continue testing the rest of these and determining which ones were. I believe x minus 1 is a factor, and try and stumble upon our answer that way. Or we could take, and now that we know that x plus 2 is a factor, we could use long division and the process that we completed before to help us find other factors. And we would just work our way down. In part 2, we are going to look at what happens when we have more complex binomials, and those would be examples such as, what if we have 2x plus 1? And is there a quick way, or do we always have to use long division? And we will find out that there is an alternative method, which is much quicker, something called synthetic division. And that will be the focus of part 2.